Hello everyone, welcome to my talk, Dancing Streams in Merging Halos, Effects of Major Mergers on Stellar Streams. My name is Sachithra Weerasooriya and I'm a graduate student at TCU. And this summer I worked with my amazing mentors, Jessica Starkenberg, Helma Koppelman, and Catherine V. Johnston. So before we go into much detail about this project, let's remind ourselves what streams are. So what is a stream? Now here you can see a stream orbiting our Milky Way. So a stream is a group of stars that's orbiting around a parent galaxy. And it's most likely these streams, this group of stars are unbound from the parent halo due to some disturbance, like a tidal disruption. So why should we care about these streams? We can use them to constrain halo masses and probe galaxies' history. And also we can use them to detect dark matter substructures, like dwarf galaxies, which are faint and because of that harder to detect. And also the impact of halo mergers on stellar streams still remains unexplored. But studies by Akal et al. 2019 and Ship et al. 2021 have looked into the effects of the LMC on streams. So this is something that we are interested in looking into. And the main question that we are trying to address in this project is that how are streams affected by these merger of two galaxies? So the main goals are to characterize the differences in morphology and structure and survival of these streams, and also to identify the possible dependencies on orbital properties and location and their ages. So how do we simulate this scenario? How do we go about it? We do this in several stages. So let's go over them one by one. Starting with generating the initial conditions for the streams and the two halos. So we generate the initial conditions for the streams in a very systematic manner so that we know their exact masses, their ages, and their orbital properties. So we have two kinds of masses, 10 to the 4 solar mass streams and 10 to the 6 solar mass streams. And also we have streams of different ages, spanning from 0.5 to 6 giga-years. And also circularities spanning from 0.5 to 1. And we also please start them at apocenters from 30 to 100. So that way some are in the inner orbits and some are in outer orbits. Okay, so now you have an idea about the initial conditions. So if you look at them in the energy diagram, here you have the total energy, kinetic plus potential energy on the y-axis. And on the x-axis, you have the circularities, which is a measure of how circular the orbits are. And if you look at the left-hand side, if you have negative circularities, you have retrograde circular orbits, and then close to zero, you have radial orbits, and on the positive side, you have prograde circular orbits. And each of these dots in the energy diagram shows you the mean energy of each of those streams. And they're color-coded by the apocenter radius. So now that we have all the initial conditions for the streams, we can create streams. So for creating the streams, we use the Gala stream generator by Price-Whelan et al. 2020. And we have a set of 1,024 streams in total, with each stream having 1,000 particles. So now we have the streams. So we locate them around the major parent halo, which is about the size of Milky Way. And we let another satellite galaxy that's 1/5 the size of the Milky Way merge in a simulation. So the simulation is run on Gadget 4 by Springer et al. 2021. We ran a set of simulations. Out of those, let's focus on the highest resolution simulation that we have. So in that simulation, we have a host of 10 million particles and a satellite of 2 million particles, and streams containing 1 million particles in total. Okay, so now that we have looked at the setup, let's look at the exciting part, which is the results. Starting with simulation. So on the left-hand panel, we have the XY in XY plane. We have plotted how it shows how the two halos merge with each other. And on the right-hand side, we have a set of streams selected and how the streams are affected by this merger. And you can see around 2 giga-years, the streams are starting to feel the effects of their merger. And they are somewhat pulled out by the effects of the gravitational potential of the satellite. And some are even trying to escape the orbits to the outer parts. So yeah, so that's affecting the shape and structure of these streams. So now we have somewhat an idea about how the merger is going to affect our streams. Now let us look at their orbital properties. Starting with circularity. So again, to remind ourselves, it is a measure of how circular the orbits are. So if you look at the initial distribution of circularities, we have a circularity spanning from -1 to 0.5 and 0.5 to 1. And this is, we have the same distribution for the simulation without a merger and with a merger too. Now, if you look at the simulation that's run without a merger, with just one halo, the distribution of circularity still almost remains the same. There are a few little differences, but it still remains the same. But if you have two halos merging with each other, the final circularities changes drastically. So the takeaway point here is that orbits deviate from initial circularities after the merger. So does this look familiar? Going back to our initial energy diagram, we have the energy versus circularity diagram, and each spot shows you the energies, and each spot shows you the star particles and their energies corresponding to those. And they're color-coded by the epicenter radius. Now this is what we have initially. Now let's see what happens after the merger. That's after about 6 giga-years. So after 6 giga-years, this is what's going to happen. The energies of star particles get dispersed around their initial energy values. So if you look into this, a little zoom into just the streams that started at epicenter of 30 kiloparsec and 100 kiloparsec. In the beginning, you have the energies correspond to their epicenter radius. So if they were in lower orbits, they have lower energy. And if they have higher orbits, they have higher energies. So what happens is after 6 giga-years, the inner orbits gets disturbed the most. You can see the energies of star particles in the inner orbits gets dispersed more compared to the outer orbits. So the takeaway point here is that energies of streams in inner orbits gets more disturbed, potentially due to the effects of merger and the gravitational potential of effects of the gravitational potential of the satellite halo. Now, if you again zoom into the outer orbits and look at those streams and color them by their ages, now yellow being the oldest streams, star particles. And we can also categorize them into just look at the youngest and oldest streams. One thing to remind ourselves about the youngest streams is that they're in physical space, they're very short. So the star particles in the streams are affected in a similar manner to all the particles. But all the streams are thin and long, so they're affected differently to different parts in physical space. So keeping that in mind, let's see what happens. So as expected, younger streams don't change their energies much. But the older streams, because of the reason that I told you just before, the energies of star particles disperses more. So the energies of all the thin streams are scattered after the impact. Now, again, if you look at the same diagram for the same streams, but color them by their circularities, you can see that the circularities for the prograde circular orbits. So the circularity, if you have bluer color, the initial circularity is more circular. And if you have low circularities, you have greenish color. So you can see some of the stream star particles that had prograde circular orbits have lost their circularity here. So some streams with prograde circular orbits become somewhat non-circular. So in conclusion, orbits deviate from their initial circularities after the merger, and energies of streams in the inner orbits gets more disturbed, and energies and circularities of all the thin streams are scattered after the impact. So to remind again, going back to the goals that we had, the main focus of this project was to look at the effect of mergers on streams, and we had with the goals of characterizing the effects of morphology and structure and survival of the streams, and to identify possible dependencies on orbital properties. In future, what we can look into to achieve these goals is to look at these streams in action angle space and look into prograde versus retrograde motion and the location of the streams near that merger event happen, which we already started looking into, and quantify the effects of scattering energy, circularity, and masses, etc. And again, running more simulations with different mass ratios for the satellite galaxy. And yeah, so as an extra special treat, I have an ATOF projection of the set of streams that you saw earlier in the simulation projected here. Yeah, and I'd like to thank my mentors, Jitska and Helmer and Catherine for being amazing mentors, for their guidance, and all the other mentors at the Galactic Dynamics School. Everyone was there, all of you were really kind and very helpful. And my fellow graduate students at the Galactic Dynamics School summer program for keeping me sane and being amazing friends. I had a lot of fun and an amazing time. and also Juan and Christian for helping me with the practice talks. Yeah, thank you very much.
Thank you, Sachi.
Yeah, that was great, and beautiful visuals. You had at the beginning like the different types of science that we can do with streams, and I'm just wondering like what about like the stuff that you've looked at, like what of those science goals do you think this kind of thing affects the most and like makes you most nervous about, I guess?
Can you say that again?
Like because like we know we've had mergers in the Milky Way, and like how do you think that affects like the type of science we can do with streams?
I think the studies that were already like that I mentioned in Ship et al. And Urkel et al. Like looked into measuring the mass of LMC by looking at the velocity kicks that's from the LMC, and use those proportion to on the streams to calculate the mass of the LMC. So yeah, yeah, but yes.
One of the deviations can be a positive thing.
Yeah, which is interesting. Yeah. So do you think that like how well do you think we can constrain those deviations?
I'm not exactly sure, but it would be interesting to look into.
So it seems like the streams that you generated were largely representative of globular cluster streams. Do you think that anything changes if you consider instead like galaxy streams because they have, velocity dispersion, things like that you wouldn't necessarily see in a globular cluster?
I haven't really thought about that, but that would be interesting to look into. Yeah.
Thanks, Sachi, for an awesome talk. I was really struck in your movie by that stream that just really took off, like that was just not even around the galaxy anymore. And I was curious, is that something you saw often? Should we be looking for like rogue streams that are not near galaxies? I was just curious if that was something you saw a lot, or if that was just a really weird case, and if you understood kind of how that happened.
I don't know, actually. I didn't have much time to look into that. So
makes sense.
Yeah.
Cool.
Yeah.
Think about just getting Emily knows what I'm going to say. Do you want to say it, Emily? If we think about future surveys, we're just getting to the outskirts of galaxies, and we don't know about the streams at 100 kpc. If they're really out there, and then past mergers have launched them, then think about looking in the local group. That's what we're going to be able to do, is find stars in the middle of the local group out to a megaparsec, not around galaxies. So it'd be really fun to, get an answer to that question. And if we could see coherent streams, that might tell us about past mergers or something. Ooh. Interesting time. Actually, you know what? Sorry, I just want to say this. I don't mean to take over. I had fun with this project, but I was like, well, the LMC is not that big, and other major mergers were so long ago. What's this gonna, where's the application going to be? And this question is making me think the application could be, can we use this to make predictions for the Gaia-Enceladus merger? Can it have thrown streams out into the local group, and what's the chances of finding coherent things? Not in density. I think you'd have to do. Anyway, never mind. Right, Titska's going.
I just, Catherine, can I just react to that? Because yes, was one of the motivations for doing this project. But even more simple, if there are streams that are older than Gaia and Enceladus, would you be able to observe them? Like, are they completely messed up because of the merger or not? And the same for the future. If the LMC merges with the Milky Way, what is left? But also taking that to external galaxies, they have a different merging history than our Milky Way. So how does that affect what we expect to see in their stellar halos?
I was looking at this, and I have one question, which is, how did you decide how large? I mean, it looks like they're both spherically symmetric in this merger. You said two spherically symmetric. How did you decide how big to make the merger? You know, what was the ratio of the masses? And then I have a comment that was based on this discussion, which is that if it really messes the streams up that much to have a major merger, you might be able to figure out how long ago each of the streams, how long they've been making streams, and then set limits on how much major mergers have, when's the time frame for the last major merger in any particular galaxy, I guess was one thing I was thinking about. But how did you decide to set the ratio of masses?
I think to pick a satellite galaxy that's a little bit larger than LMC to see the effects, to observe the effects of the merger.